going to start the recording here. We're going to do an example from section 5.10. I am pleased, so we are recording now. I am pleased with how your work's going though in 4.5, and there was some good discussion here, which is why I like to have some classwork time. We've been spending some of our class time, sort of, this is your, first time you're taking an exam with me, so there's some, students have questions and I like to clarify things. So that's been taking up a little time. I'm thinking hopefully in the future we'll have more classwork time. But at any rate, we had some today and that's good. Okay. Now, okay, so I'll reactivate the assignment, don't worry. So we want to find out, we have here what's called an improper integral. An improper integral. Okay. And we may not finish all this problem today, but we'll at least get some of it done. Section 5.10 tends to be difficult for students, but I would love it if it weren't difficult for you. Okay. So let me give you a moment to copy this down. Okay. So, all right, you have a lot of expertise with integrals. And up to now, all your integrals have been, proper integrals. But now suddenly section 5.10, we have something here. We have an integral that they call improper. Okay, this integral is from negative infinity to 0 of x times e to the x dx. And they're calling it an improper integral. Why is that improper? What makes this integral different from what you've seen in the past? That's right, Rodrigo. The negative infinity as one of your endpoints. So you're used to doing integrals. You're used to integrals from a to b, for definite integrals, I should say. You're used to integrals from a to b, f of x dx. And you're used to finite values for a and b. But now we have an integral that has the left endpoint being negative infinity. And then we're going to ask, does the integral converge or diverge? Converge, by the way, means that the area is finite. We do recognize that this integral, it's a definite integral, so it represents the area between the x-axis and the curve x times e to the x. represents that area. The area goes from x equals 0 to x equals negative infinity. So it's an area. And if the area is finite, the area, we say the integral converges. But if the area is not finite, we say the integral diverges. Of course, if the integral converges, then we're going to evaluate that area. Okay, so I drew a picture here, I think a helpful picture. May I move to the next page? Are we good so far? All right. Thank you, everybody. Okay, so we go to the next page. And what I've done here is I've drawn the function x times e to the x here. And I'm drawing the function from x equals 0 to negative infinity. Or I might say from negative infinity to x equals 0. And what we want to do is we want to find this area. The area between the x-axis and the function. And we know the area is going to be negative. But the question is the area finite? Because we know that this function, we know that we're going to negative infinity. And so there's always going to be a little bit more area as we keep drawing the curve out to negative infinity. There's always going to be a little bit of negative area that's going to accumulate. The question is, at what rate does this area accumulate? Does it accumulate so fast? Does it accumulate fast enough so that the area is infinite? Meaning, you know, like infinite area, meaning like negative infinity, because we know the area is negative here. Or does the area accumulate at a slow enough rate so that we get a finite answer? That's the question. Is the area finite? So how do we handle this? How do we handle an improper integral? Well, first thing I do is I set the integral equal to I. I'm always used to doing that. But we have to write the integral then. All the techniques you learned from chapter 5 deal with definite integrals. Integration by parts, substitution, partial fractions. They're all definite integrals that those techniques work with. So the way I'm going to get around this issue where my bottom limit is negative infinity is to express the integral I, as the integral going from t to 0, not negative infinity to 0, but t to 0, of x e to the x dx, but then letting t go to negative infinity. So what I'm doing is I'm writing this integral as the limit of a proper integral. The integral from t to 0 of x e to the x dx, that's a proper definite integral. And I can use any of my integration techniques on that because t is finite. However, what I'm going to do is let t go to negative infinity. And so then the limit as t goes to negative infinity of the integral t to 0 x ex dx, that's the same as my improper integral. It's going to get me the same answer. And we actually, we call this a type 1, incidentally. This is a type 1 improper integral because we have an infinity, well, negative infinity, as one of our limits. But anytime you have an infinity or a negative infinity as one of your limits, you have what's called a type 1 improper integral. So what I'm going to do is I'm going to evaluate this limit so I can determine the integral. But of course, I'm going to have to use integration by parts on my integral in order to find out what the antiderivative is. And you know how to do this. You let u equals x and dv equals e to the x dx. So then v equals e to the x. And so my integral can then again be written as the limit as t approaches negative infinity of my resulting of my result. Okay. Okay, so we get to here. Are there any questions so far? Okay, so it's like we're doing an integration by parts problem. It's just our bottom, our limit, one of our limits is t, but we're going to let t approach negative infinity. But first we have to figure out the complete antiderivative. Okay, we have to figure out the complete antiderivative before we take the limit. So the integral of e to the x dx from 0 to t to 0, I should say, that's the antiderivative of e is e to the x from 0 to t. And so my integral I can be expressed as the limit as t approaches negative infinity of negative t times e to the t minus the quantity e to the 0 minus e to the t. Are there any questions up to this stage here? Up to that step? All right. Good, Tina. Good, Eric. Good, Surfiel. Okay. All right. So now we have to take this limit. Okay, and we're letting t go to negative infinity. Is e to the 0 going to be a problem when we take the limit? Is e to the 0 gonna be a problem, or is that okay? Well, e to the 0 equals 1, right? So that's not even involved in the limit. What about e to the tth power? E to the tth power, as t goes to negative infinity, what would e to the tth power approach? That's going to approach 0. That's right. So that's not going to be a problem. And I'm going to sum this up very shortly here because I know it's 5:10 now. But this negative t times e to the t, is that going to be what kind of form is that? Negative t times e to the t. I mean, even forget the negative, but t times e to the negative t. T goes to negative infinity, and e to the t goes to 0. Okay, so you have negative, that's right, Colum, negative infinity times 0. What kind of form is that? That's called a, what type of form? Is that a determinate form or an indeterminate form? Indeterminate. What special rule are we going to have to use to help us figure out this portion of the limit? L'Hopital's rule. That's right, Colum. Very good. So what we're going to do then is, when we continue this problem on Thursday, we will take it from this step here to try to see what this integral is. Are there any questions so far on what we've done here? Are there any questions? This is why, by the way, you needed to learn L'Hopital's rule. Another reason is because it's used in section 5.10. Are there any questions at all?